All right. So static electricity, where have you guys heard that before? What examples of static electricity exist in your everyday lives? Your hair? What about your hair? When you rub it against a balloon, does anyone wake up in the morning and feel like there's a rubber balloon in the air and they're just rubbing it? No one does that, but your hair does get messy. Anyone have a quote-unquote bad hair day? Yeah. Bad hair days, I mean, there might be more to it than I'm talking about, but the physics-wise, let's say there's a very humid day, there's a lot more static electricity in the air. Oh, that's going to happen often. I still haven't figured out how to not rotate this thing. When there's humidity in the air, there's more static electricity, so there's going to be some interactions with your hair. We'll talk about what that is. And then your hair ends up not behaving correctly because it's repelling against each other and being attracted to other things. Yeah, so bad hair day, hair against the balloon. What else? Yeah?
When you like touch someone or you touch a door.
Yeah, exactly. If you have touched a door handle and you get a shock, that's an example of static electricity. What's a really big example of static electricity? Lightning, yeah, absolutely. So, anyone who watches Family Guy? No one? Family Guy? There's like 3 or 4 seasons ago, there was this episode where Peter gets like these pajamas, these onesie pajamas, and he's walking around the carpets everywhere and shocking people. So you're rubbing your feet against the ground and you can shock people. What's the friction happening when it's dealing with the clouds and the lightning and all that stuff? Okay? The question is, Peter rubs his feet on the carpet and gives people shocks. What is the cloud doing to give us a shock? What's rubbing up against what? Yeah. Exactly. It's rubbing up against molecules of air. Not just air, but also, because it only happens on humid days, water, yeah, exactly. So it's molecules of water that are rubbing up against each other, generating a static charge. And then once that charge becomes too strong, it discharges, wham, it's in the ground. Any of you guys live in NDG? Yeah? Your house okay? Okay. Which part of NDG?
Like right in the middle of where it happened. But
oh yeah? So like near Decatur, near Giroir? Yeah, so those of you who might not know, 2 days ago, not yesterday, but the day before, there was like a windstorm. It was like unheard of. There was like trees ripped to shreds, like huge amounts of wind. I saw trees like this thick, totally ripped off from underneath the ground. There was this one street in NDG called Prud'homme, where there's a KFC, I believe, on that corner, and just below Sherbrooke there's a tree that's totally fried. Like it was a lightning strike, hit the tree fell across the street, crushed a car and part of a house. It was pretty intense, and that was from a static electric charge. So pretty heavy duty things that are happening there. You do not want to be on the standing end of that. Any other examples of static electricity? Yeah?
sheets in a dryer.
Sheets in a dryer? Yeah, absolutely. If you take out your sheets, they're kind of like stuck together. Or if you take, have you ever played with those, not played because no one likes these things, but you know, like packing peanuts? They're not actual peanuts, but like there's stuff that you put in boxes to like protect things when you're shipping them. Those things that get stuck to everything, that's all static electricity. There is no actual electricity, there's no current going in there, but it is static electricity. Okay, so let's talk a little bit about this. When I say static electricity, what word shows up that might describe what it is? Static. What does static mean? Not moving. Okay, what would be the opposite of static? What's that? Elastic? Elastic in physics has a different term. Kinetic. Okay, kinetic. And we don't refer to, there is no such thing as kinetic electricity. There is another name we give it when it's kinetic electricity. When it's a flow of electrons, we call these current in a circuit. Yeah, currents in a circuit. Yeah, that's the flowing or the kinetic part of electricity. So here we're dealing with only static electricity. So if we had to talk about this, these are your objectives for today, analyzing situations where you can apply this and trying to describe things with your knowledge. There's a history. I'm not going to go over this because we're going to automatically go through all this because every one of these people discovered something important that's important to the course. But just so you know that electricity started back in the 1700s, and that's a long time ago. Most of us think of electricity as like maybe the late 1800s in the Industrial Revolution or light bulbs finally, but it's actually quite a bit older than that. So we talked about it. Static electricity occurs when there is a buildup of electric charge on a surface. Right? So when it's the lightning striking, the buildup of the charge is building up in the clouds. And then when it gets too much, it discharges into the ground. When you're touching a door handle, it's because the door handle had a buildup of electric charges, and when you touch it, it discharges into your hand. Okay? And it's called static because the charges don't move. That's important. And finally, your laptops, your cell phones, all that stuff, those are using currents, and that's not static electricity. So those won't be under this section of the course. Any questions about that so far? Just trying to remember names again. Elizabeth? Zach? Sabine? Coralie? I'm sorry, I forget you four. What's your name again? Valerie? Alex? In the back there? Noemi? And? Gabriella? Okay. I might still forget some of those. I can't remember either. Which one? Gabrielle? Margot? You're Kevin? You're Cedric? Isabel? Oh yeah, Isabel, I remember because we had that thing. Okay. Okay. Moving on. When we're talking about electricity, we have to talk about charge because remember, it's a buildup of charge. Right? The more charge there is, the more powerful that discharge is going to be. So we need to be able to quantify charge. How we quantify charge is through electrons and protons. Those are the things in atomic theory and all that stuff that contain a charge. And so we need to understand those the most, because really, that's where charges come from, protons and electrons. One electron has a charge of -1 charge, but that's not a realistic amount. No one ever measures anything in electrons, the amount of electrons, because it's so tiny. One electron is so tiny, there's no point. Kind of like one atom is so tiny, right? Like one carbon atom. Who cares about one carbon atom, right? So we came up with something more convenient to call it a mole. And we say a mole of carbon atoms is 12 grams. That's something more real to us, right? And it's the same thing here. One electron is too small for us to measure, so we came up with something called a coulomb to quantify that, all right? And we call 1 coulomb as 6.2 times 10 to the negative, times 10 to the 18 charges, all right? So that's a big amount of electrons, makes 1 coulomb. And a coulomb is actually something that's real. You do not want to get shocked by 1 coulomb of charge. In the case of an electron, I put a minus in front of it. Does that mean it's a vector? Remember what vectors are. What are vectors? Direction and measure of magnitude. Okay, that's what a vector is, if you guys remember that from mechanics last year. Is charge a vector? Because I put a negative in front of it. Absolutely not. It's not. Because there is no direction to it. It has a negative and a positive, but that's a sign convention that we use mathematically to determine whether it's a negative charge or a positive charge. Okay? So if an electron is negative 1.6, and a proton is the exact opposite of an electron, what would be the charge of a proton? Which is what? Yeah, 1.6 times 10 to the negative 19 coulombs. All right? So I have that written here. This is the charge, or the coulombic charge of one electron or one proton. This is referred to as the elementary charge. I had that on the previous slide here. This is known as the elementary charge. It's right there at the bottom. right? And if I go to the next slide, these are both examples of elementary charges. All right. Now again, remember that this is the charge for one electron. So if I were to ask you a question like this, would you be able to tell me how many electrons or protons there are? So a balloon holds 8, by the way, what's that symbol here? Micro? What is that value in terms of regular units? Oh, good. You guys are good. 10 to the minus 6. So 8 times 10 to the minus 6 coulombs of charge. Positive 8 times 10 to the minus 6. All right, so these are going to be protons. So how many protons are there? Could you guys do that calculation real quick? It's kind of like a unit conversion. Think of it as you're calculating the number of moles in atoms. So while you guys are doing it, I'll do it here too. Please don't look at the board. This is something everyone should be able to do now. When you have an answer, I'll take it. Yeah. Yeah, sure, give it to me. What are the units? P plus. That's just some, whoops. I'm going to do something while you guys are doing that. Yeah, so 5 times 10 to the 13 protons, okay? So don't forget the units. This is a science class after all. We're sticklers for units. I will definitely not give you chances with that. Always, 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 always remember your units. By the way, do you guys know scientific, not scientific, what's it called? Significant figures? Calculation of significant figures? Yeah? Okay, if you don't, please brush up on them. Come and see me if you don't remember them. You need to do them in all your problems in all your labs. Okay? Are we okay? All right. So I want you guys to complete these 2 sentences. Most objects do not contain any charge. For example, this object right here, this pen, this table, this, you, and everything, do not contain any charge. What does that mean you are? Neutral, absolutely. What does that mean? To be neutral. You can say it in 2 different ways, but it means something to be neutral. Yeah? You don't have a charge. Say that more scientifically. I'll start with what you said at the beginning. You said the charge is 0. Does that mean I have no charges at all? Or is it that it's balanced out? That means the net charge is 0. Okay, so neutral means that Q net, by the way, Q is a symbol for charge. Q net is equal to 0. Another way of saying that is what? Kevin, you had your hand up, I think, or someone over there? No? What is that also saying? Q net is equal to 0 can also mean one other thing. Absolutely, exactly, right? So that also means that the number of protons is equal to the number of electrons. That's what it means when something is neutral. Any questions about that? Pretty straightforward. If you have a deficit of electrons, that means that you are positive, because you have not enough electrons, so that means you're positively charged. If you have extra electrons, you are good, negatively charged. Simple as that. Here's when we get into a little bit of logic, and this is what's going to lead us into our next activity and the activities after that, and then probably the first big mathematical part of this course, is when we talk about two oppositely charged particles. So let's say we have a proton and an electron. What's going to happen between those two? What is that? Attraction. There is something that's happening that's attracting these two subatomic particles together. So electron and protons have got attracted together. So they attract each other. We can write that. Each other is two words, isn't it? Each other. However, it's not as simple as they attract each other, because what attraction is not a term that we use in physics. What is a more accurate word to describe what's happening between a proton and an electron that causes them to move towards each other or to get attracted? I don't want to say the word, but you know which word I'm talking about? Forces. Not electromagnetic, because there's no magnets involved, but forces. All right? There's a force that's causing these two particles to be drawn towards each other. And the name, it's not electromagnetic, you're close, is electrostatic forces. Okay? So this is what we call Fe. So electrostatic force. Oops, that's L, electrostatic force. And a guy named Coulomb is the one that came up with this. So this is Coulomb's law. And we're going to talk about that next class. Okay? If I were to put it the opposite way, two similarly charged particles are placed next to each other. What do they feel? Repulsion, absolutely. We're okay with that? And again, that's still Coulomb's law. Yeah. So far, so good? Do you guys feel like I'm going too fast or too slow? A bit too fast? Okay. I think that causes balloons. Okay, yeah, so these here are just examples of where you might see static electricity. We talked about them: balloons sticking to walls, your hair standing on a bad hair day, the electric shock you sometimes get from a door handle. And I have some demos here for you. Now, there is a slide I'm missing here, and that's strange. I'll bring it up later. All right. So, actually, you know what? I need it now. So you guys don't have this slide. I'm sorry about that. I'm going to have to Google it. But I'll add it in afterwards when I upload it so that you guys have it. It's something called the triboelectric series. Have you guys ever heard of this? Triboelectric series. Images. So it's a list, basically. Let me pull up a nice one. Let's do this one. Again, I'll upload this onto your PowerPoint later. It's just because we need it right now for the demo that we're going to do. Can I have a volunteer or someone with long hair. It cannot be me. Someone with long hair who doesn't mind getting their hair messed up. Anyone? Any volunteer? You're gonna get your hair messed up. I can't do the demo without a volunteer. Thank you. All right, so we need to make some observations. So right now I have a balloon. No one has hair. And is the balloon attracting the hair? No? Is there any interaction whatsoever? So if there is no interaction whatsoever, that means there's no electrostatic force between them. You guys agree with me? What can you tell me about the charges of her hair and my balloon? Neutral? 0. Okay. So this has a neutral charge, that has a neutral charge. We're going to change that. May I rub on your hair?
Huh?
Can I rub it on your hair?
Yes.
Oh, if you want to see it. Okay, so tell me, what kind of forces exist now? Is it attraction or repulsion? Between what and what? The hair and the balloon, there is an attraction. Okay. So does that mean something is charged? Yeah, of course, it has to be. That's the reason we're doing static electricity. It has to have to do with charges. So is the balloon charged? Is the hair charged? Or are they both charged? Both charged, because if only one was charged, the other one was neutral, there'd be no force, right? Both have to be charged in order for there to be a force. What's negatively charged, the hair or the balloon? Now we're getting into harder questions. So now you have to look at the board. So the higher up you're on the list, if you're positive, that means you're positively charged. So in this case, what's higher up, balloon or hair? Hair is higher up, so that must be positively charged, and therefore the balloon is negatively charged. Okay, thank you very much. You can call me. I'm going to mess it up again later. So tell me a few things. It went from being neutral and it went to being charged. So what happened to the charges? During the friction, when I was rubbing it, what happened to the charges? Where did what go? What do you think?
Electrons.
From what to what? The hair to the balloon, exactly. So the electrons went from the hair to the balloon, all right, leaving the hair to be positive, right? And because the balloon got all the electrons, it became negative. Is it possible that the protons went from the balloon into the hair? Why? Your answer is right. It's not possible, but why? Because what? Exactly. They're in the nucleus. When you're talking about, let's say, Naomi's hair is made up of which atom? What makes up hair, by the way? You guys know that? Biology answer question. Keratin, which is a protein, and proteins are made up of? Amino acids are made up of which atoms? Go. Nitrogen, carbon, hydrogen. Keep going. Oxygen. Someone else? The acronym is SHNOPS. CHNOPS. Right? So oxygen, phosphorus, sulfur, those would be the ones that are there. So Naomi's hair is made up of those atoms, right? And if I want to take a proton away from carbon, is it a carbon anymore? No, it's the number of protons that determine what atom it is. Right? So Naomi's hair didn't go from being carbon to being, what's before carbon? What's before carbon? Boron. It didn't go from carbon to being boron. Her hair didn't change its atomic composition. It's still carbon, it's just now it has less electrons. So protons cannot move. We're going to talk about that throughout the whole course. And when we do circuits, it's going to be the total opposite. But when it comes to electricity, we're talking about the movement of electrons, and electrons are the things that are in it, not protons. Okay, so nope, that's not what I meant to do. I want to go back here. All right, so you said that the electrons left by the hair went to the balloon. The balloon is now negatively charged. What is the hair? Positively charged? Okay. Is there any repulsion happening? So you said the hair is positively charged, the balloon is negatively charged. Is there any repulsion? Hey? I can't hear you guys now. No repulsion? What do you think? It hasn't to do with that, but there is some repulsion. I'll give you that. Yeah.
There's some repulsion because there's some protons and electrons.
Say that again.
There's some protons and electrons on both ends. So the protons and electrons.
Okay. So you're saying between the balloon and the hair, there's still some repulsion there? Yeah. But overall, it's attraction, right? Yes. Okay, overall it's attraction. But I'm talking about, is there something that's overall repulsion? There is. How many hairs does Noemi have? More than one. Are they all positively charged in that area? Yeah, of course. There wasn't just one strand of hair getting attracted to it. So all those hairs that were going up, they were all positively charged. So all those hairs are repelling each other, right? Because they're all positively charged. Right then. I left the empty space here for you guys to work with, okay? Explain this observation in terms of the movement of charges and things like that.
Repulsion between the negatively charged atoms of the balloon.
Say that again? Oh, the charges themselves.
Yeah.
Yes, but they're all being attracted by the positive charges of the hair, so they're all still close to each other. Yep. It's a good question, because it's going to be important in our next step. So here's what I wrote. I'd like to get someone's answer, though. Oh, thank goodness. Okay, so let's go to the next demo. It's going to get a bit more interesting. It's over here. I have one of these. You guys know what this is called? A what? Tesla coil? That's not necessarily the... that's something else. That's something else. This is called, everyone should know this. Come on, it's a Van de Graaff generator. Duh. I'll write that on the board. Van de Graaff. So this is the Van de Graaff generator. When I turn this on, you can see that there's a belt moving up and down here. All right, and that belt causes friction internally, generating some static electricity. Positive charges are flowing upwards, so this thing becomes massively positively charged, and the electrons are flowing through this wire and out the plug through the, what is this thing called? This third prong. You guys know what that's called? That's a ground. Okay? And you guys did this in secondaire 4. Did you have a ground in your circuits? Okay, so some appliances will have a ground. Some don't. Older things tend to not have them. New things tend to have them. Your electronic devices probably won't have them because of a reason you'll understand later when we do circuits. But essentially the negative charge is escaping into here. So what leaves behind is just this positively charged ball at the very top. All right, and so this is positively charged. And actually, if you guys can see it, it's attracting my hair right now. You guys see that? Weird. Okay. And this here is same material as this, and this is a plastic insulated material, so I don't get shocked when I hold it. All right, and I'm going to bring this close, and you might hear some shocks. You might even see some shocks, but that's not the point. I'm going to ask you a few questions. All right, this is neutral. All right. What's the charge here? 0 charge? Okay. What's the charge? What's the charge? Neutral. Okay. Nothing has happened yet. Maybe it's not because of how close I am, but essentially it should still be neutral. As I bring this closer, but I don't touch it, I'm not touching it, if I bring this closer, what's happening to the electrons or protons or whatever? What's happening with the charge of this ball? Is it still neutral? Remember, I'm not touching it. So is it still neutral? You guys have to answer your yeses and no's much louder because now this thing is on, I can't hear anything. Is it? Yes, what? Yes, it's neutral. Overall, it's neutral. But there's something that's happening. This is a conductive material. In a conductive material, electrons are free to go wherever they want. All right? You are? You snap? Okay. Have a seat. You're not on my class list, so did you switch from another class? Yeah. Okay. Which class were you in before? No, I mean, which physics group were you in before?
I just had this class.
Oh, okay. All right. Okay. So, I'm bringing this close, and remember this is a conductive material. Conductive material means that the electrons are free to move within the material. So I bring it close, what's happening? Electrons are what? Are coming through the, oh, Jesus Christ. Excuse my language. The electrons are getting closer to the part that's closest to that. Oh, you know what, because my hands are wet and it's creating crazy stuff. So the electrons are getting closer to this end, meaning that this end is what? Positive, all right? Overall, it's still neutral because it didn't lose any electrons to it, but overall it's neutral. The net electrons are on this side, and the protons are on this side. When I take it back, what's going to happen? Still neutral. The electrons and protons, they attract each other again, and they're all back into the same configuration as they were before I turned anything on. What happens if I now touch this? What's happening now? What's discharged? What's that? The charge, which is what? The electrons from the little ball, because it's in contact with the Van de Graaff generator, the electrons have now left the little ball, entered the big ball. So now if I take this away, what is the charge of this thing? Positive. Right? I removed the charges from it. Okay? So far so good? Let's try some. Hopefully. You guys might have to move a little bit in order to see it, but there we go. Oh, you can see it a little bit. Let me try that. There you go. You guys see that? You guys see how it's attracting the water? Why is that?
Water is polar.
What does that mean when water is polar?
One side is positive.
Yeah, one side is polar. So water is like partially charged because it's not a big molecule, but it's big enough that you have a positive end and a negative end. So this is, what charge do we say this was? Positive. It's attracting to the Which is what molecule? Which atom in the molecule? Oxygen, exactly, because oxygen is more right on the periodic table, and therefore more electronegative. So it's attracting the oxygen atoms that are more electronegative to this thing. That's why the water stream curves around it. Write that down. I'm going to abbreviate the Van de Graaff generator as VDG, okay? Try to write it in your own words, because writing it in my words might not mean anything to you. Okay? Definitely put drawings, because they're super important. I'm going to need you again after, okay? Yep. Oui. Si je le touche, qu'est-ce qui va arriver? So là, il est positively charged. If I touch it, what's going to happen? My electrons, it's going to take my electrons and make it neutral. And that's why I get a shock when I touch it. And where now what charge am I in? Positive. Where am I going to get my negative charges? From where? From somewhere. I'm going to get another shock later. Might not be one that I'll notice. I got it from the ground, because the ground, the planet, whatever, has so many charges that if you take away one charge or 10 charges, it's still pretty much neutral. Yeah? That's a very good question, because I'm going to have a follow-up question for you guys after. Can someone read me their answer? Please, please, please. Please share. Share is caring. Who came up with that expression? Sharing is caring. Anyone want to share? Otherwise, I'll make some. And I can only remember the ones whose name I know. Okay. Okay. It becomes neutral after I touch it, and it steals my electrons. Okay. Perfect. Very nice. Thank you very much. I have a follow-up question for you guys. Let's do it a little bit differently. What is the charge of this? Neutral. What's the charge of this? Okay. What's the charge? Positive. What's the charge of this? Overall neutral. What's on this side? What's on this side? Watch what I'm going to do differently. Okay. What is the charge of this thing? All right, I need some hands or I need some answers. Yes, what do you think? Was the ball touching that? Okay, you can see it. Okay. Let's do it again. So, everything is neutral. Okay. All right. So, it's not touching. The electrons are on this side, and this part now is positively charged. I touch it. So I didn't touch this with the ball. So what charge is this? Who said negative? Can you explain to me why?
Because your hand, well, the rod might have attracted the electron from the hand.
Absolutely. Which part did I touch? Did I touch the positive side or the negative side? I touched the positive side, so it's attracting the electrons that are in me to go into here. But it never lost those electrons to the Van de Graaff generator. They were just stored on this side. So now I touched it, it took my electrons, I moved it away, and therefore now the electrons are all back together, but there's more electrons because it has the ones that I gave it to. All right? That's called induction. We're going to learn about that a little bit next class. But essentially now I have this negatively charged thing. So hold on, let's do it again. Let's do it all normal. Okay. All right. I just needed to ground myself, so I got to touch things. Okay, perfect. So now we're going to do the same thing. I'm going to touch it. Oh, Jesus. That's so good. All right, I gotta restart. Every time that happens, I got to restart. When that shock happens, what does that mean? There's what? Discharge. Why is it discharging if there's no contact? Eh? What's a conductor in the air? Water. It's a humid day, it's been a humid week, and I'm sweating my hands. And so there's just water everywhere now. It's okay. I just can't get too look. Okay, so let's restart. Okay? Alright? I'm going to do it a little bit differently now. I'm going to do this. Now I'm going to do that. What's the difference? What's the charge of this now? So let me tell you the difference. Let me show you again what I did. This is what I did this time. All right, this is the new one. Like that. Okay, so I'm there, all right, and I move it away, and then I let go, or restart. I remove my hand, and then I move it away. Okay, so it's a matter of, did I move my hand and then move away the thing, or did I move away the thing and then move my hand? So the question is, what happens if I do this? All right, I go like this. Yeah. What? C'est exactement ça. So I take away the rod, right? I take away the rod, and now this thing is still positive. It has my negative charges in it, so it's negatively charged, but I'm positively charged, so I'm going to attract back my electrons, and therefore this is going to be neutral again, theoretically. You guys understand that? Okay, you guys want to write that down? If you have questions, please ask them. Okay? It's super important if you have any questions. Yes?
So the more times I touch the rod, the more it goes back to neutral.
It depends when on where I'm touching it, right? It's not how long I touch it for, it's when and where. Both cases of touch, so now the question is when, right? So did I let go after this thing was, like if I were to not touch it, bring it back, then none of the electrons actually escape them. So the electrons that are concentrated here are not back everywhere, right? Which means that it's going to push away the electrons that it has in excess. Because now it's excessively negative. So it's going to push them back into my finger. Whereas if I had let go, those electrons have nowhere to go. So they're stuck being there, and therefore this remains negative. Okay? By the way, us doing this is excellent practice for our next test because we're doing 3 demos today, and then right afterwards I'm going to show you guys a video, and you guys have to do the same thing with the demos in the video. That means if we did the same thing like 10 times in one lesson, chances are there'll be a question on the test. Think of it that way. Whenever I'm teaching something, if I put more emphasis on something, those are the important things. You want me to add that? Review. All right. All right. So thank you very much. You can go have a seat. What's the charge in the balloon right now? Negative. So if I turn it next to the water, that's attracting it. But before the positive is attracting it. Because it's polar. Okay, remember that. It's polar. Water has both positive and negative, and so it's going to get attracted no matter what. Does that mean that water can never be repelled? Because it's being attracted to positive, it's being attracted to negative, so then it can never be repelled. Is that possible? Why? The answer, I don't know. I really don't. Maybe you guys can find that out. That would be really interesting to know. Why is it that you can't repel water? Because the molecule is not symmetrical. If it were symmetrical, I would understand, right? So let's say this is water, like that, right? Let's call this the positive end, this is the negative end. I put 2 negatives because oxygen is more negative than the hydrogen. And the hydrogens are each positive, but there's 2 of them, so they balance out. So if I were to add a positive charge here, it would attract this way. And if I were to put a negative charge here, it would attract that way. So the molecule's orientation is always this, which doesn't make sense to me logically, Why always being attracted? Because if it prefers to being pulled and the hydrogens are being dragged behind, that makes it like it should go this way. And if I were to put an electron here, then it should propel in this direction. That's what I think should happen, intuitively. But of course I'm wrong about that because our observations just showed it otherwise. Right? If you can find an answer, I'd be really interested to know that. All right. I'm going to move this because I don't want to ruin it. One more demo. So far, so good. Any questions? Seriously, any questions? I like them. I like questions. All right. Let's do it again. This time I'm going to use this object here. I'm going to touch. All right, just wait a little bit for electrons to move. Remove it. Turn it off. Actually, before I do that, let me ask you one more situation. Restart. What happens if I do this? So this is on right now and I'm touching it. What happens if I turn this off and then remove it? What's my charge here? Neutral, because this was no longer positive, so I took back my electrons and this is now neutral again. All right. Obviously not perfect, that's why you heard a shot. Okay, but anyways, making this thing positive. And then I'm going to use this. I don't know if you guys can see it. You might have to look very carefully. Did you guys see that? What's happening there? Maybe come a bit closer. You can come closer. You guys see it? And I took it away, it stopped. Bring it back. Open. Let me try one more thing. Maybe the other passes didn't work, but it's looking like it's working well right now. So if I were to, actually before I do that, explain to me what's happening. They're what? They're repelling each other. The two balls there are repelling each other. Just to give you an idea of what this is, this here is, they're called pith balls. And those are two styrofoam balls that are painted with conductive paint. And they're attached to a conductive wire that's attached to this conductive rod and that's attached to this conductive marble at the top. Everything else is insulating, so if there is a charge, the flow of electrons can freely happen through the wire from the pith balls, through the rod, and through this ball here. Okay? So knowing that, what do you think is happening when I bring my rod close to it? Why is it repelling each other?
Because the positive rod is attracted to the negative charge that's coming to the ball, so this causes the positive rod.
Absolutely. You guys understand that? No? Okay, just to repeat that. This thing is positively charged. It's going to attract the negative charges and temporarily put them in this ball up here. All right? And because the electrons are temporarily up there, that means the bottom part is temporarily positive. And during that amount of time, the balls will repel each other because you're both now positively charged. Okay? Hold on, don't go anywhere. What should happen if I touch it? What should happen before I do it? Okay, it is going to discharge. But what does that mean for me? How is that different from me just bringing it close and from actually touching it? What is an idea? What do you think? Yeah? Okay, so then after I remove it, is it still going to be repelling? Yeah, so theoretically what should happen is, now I've permanently removed the electrons, as now are here, if I touched it, leaving that thing to be permanently positive. And if it's permanently positive, whether my rod is there or not, they should still be repelling each other. So let's see if that works. It doesn't work. But it's because this thing is not the best machine. There's a better electroscope. This by the way is called an electroscope. There is one where there is aluminum foil or gold foils that are hanging in styrofoam, they're quite heavy, and gravity always beats the electrostatic force. It's not perfect. You got the idea of what it's supposed to happen. So right now, once you're done writing that, take a break, come back at 8 seconds. 8 seconds. 8 seconds, okay? Electroscope. Take 5 minutes to write this. Go and come back at 9:55. No. Yeah.
I didn't quite get the demo 3. I understand that. So does the rod, when you touch the electrode of the rod, does it become neutral, or does the electrons get transferred into the rod?
So yeah, when I touch this, it lost its electrons to there. So now it actually is missing electrons. It's positively charged. And when I touch this thing, if I touch it or if I bring it close, if I touch it, it's stealing the electrons. And this, yes, becomes neutral. Or, well, it depends if it took enough electrons, but it's becoming more neutral. Let's say we don't know if it's totally neutral or not, but if it took exactly how much it needed, then yes, it becomes
And this
neutral.
will become positive, and this becomes positive, so these voltages are going
Exactly, and it's because I permanently took away the electrons, then it should repel even after I remove my rod. Because the electrons are not here, the whole thing's positive, it's not getting them anywhere else. But because we're not in a perfect situation, it's stealing electrons from the air, and this is becoming neutral again.
Okay.
No problem. Okay. Actually, there's a couple more minutes. One more minute. Okay, so here's what I want you guys to do. There's about 30 minutes left of class, and what I want you guys to do is there's on the last slide of that PowerPoint presentation, there's a link that I posted. I want you guys in groups of 3 or 4 or alone, whatever, but preferably in a group, so that you can talk about it. Talking about it, me teaching it to you actually makes me understand it better for myself. So you guys talking about it to each other will make it better for you guys to understand. So you guys are watching this video, look at what's happening, try to explain it in the terms that we described these 3 demos, okay? Some of you might need the triboelectric series chart. I'll post one up here on the board. And when I upload the PowerPoint presentation later with my annotations on it, I'll make sure there is one in there as well, okay? So I'll post one up here. You guys can Google it too if you want, but you'll need that for that video. So do that. That's it for half an hour, and then in the last 5 minutes, I'm just going to ask you guys a couple questions, and then we'll go home, or to your next class, wherever you have.